Hello, everyone. So I'm John Oxford. I'm a software engineer at a company called PowerSecure. We do kind of a industrial IoT solution that Frank was talking about. We don't use nerves. I don't do any Elixir in my day-to-day job, at least yet. So this is a big hobby project. I've got into a lot of things I've tinkered with. So kind of the impetus for this was about a year ago. I actually met a couple people here that I've seen. I did a training class that Frank Hunleth and Justin, the co-authors of Nerves, they host that in a lot of these conferences, and they walk you through how to make a firmware bundle, push it to the Raspberry Pi, interact with some sensors, and I've messed around with a lot of Arduinos, Raspberry Pis, those kinds of things. You can find a ton of guides online. Usually you're going to be writing Python or C++. So you'll get kind of like a feel for how these things kind of work. And once I took that course, I'm like, well, I've been interested in Elixir, so that was a perfect marriage. I don't want to have to necessarily worry about installing a whole Linux operating system and then creating a systemd script to boot up my thing, because I want to stick this outside. So I'll kind of walk you through what this is. So by show of hands, anyone here who's actually used Nerves at all? So not everyone, that's good. So I'm going to walk you through a little bit. You'll see how we're doing on time. So we'll go over what Nerves is. There's two different protocols. There's more than this, but GPIO and I2C for the sensors I'm using. There's a group of libraries that you'll pull in order to interact with these kinds of sensors. Kind of what this looks all putting together. This is not just a Nerves hardware project. There's some other stuff beyond it. I'll show you some relevant code here, and then I'll demo it off. So I want to give a quick shout out to this company called Tovoltaic. Super awesome company. They're the ones who made the solar panel and the battery I'm using in this project. I went back and forth with them quite a bit through support, because I originally bought a smaller solar panel, bought a smaller battery. I had this in a different location in my backyard. They kind of did some rough estimation of kind of how big of a battery I need, how much light I need. To be able to power this thing 24/7, that's the goal, at least pretty close to it. So I asked them if I could give them a quick shout out. I'm not getting paid or anything from them. I just really like this company. You could do more customized things, but I'll show you the equipment that they offer here, so definitely check them out. So the first thing is the solar panel. So this is a 10-watt, 6-volt ETFE, which is a specific kind of polymer. You can get two different kinds of solar panels. These aren't going to hold up as long. They're a little cheaper. That was $65. I had to get a really long extension cord, because you can see this is obviously on the roof of my house here. And this is all very hacky. I did a lot of zip ties. There was a satellite dish that the former owner of the house had on top, and you can see right here, I've zip tied it up. I'm trying to get it. There's a lot of requirements my wife had too. She did not want this to be very visible and very ugly, so I have to work around with that too. So that was the first thing, all right? So I've got this up. It's pointed up mostly at a 45-degree angle. Depending upon the time of the year, it's going to be more sunny than not, so it's generally pretty good. If it's sunny, it'll charge the battery most of the way throughout the day. The battery is the other expensive thing. So these are probably the two most expensive things you'll get. The 12,800 milliamp hour battery, and that's probably good for 3 or 4 of your phone charges. The big thing with the solar panel projects like this is you need to have a battery, or you have to wire up your own regulator or something, because as the sun goes over your house or wherever you have your solar panel, the amount of voltage that's going to be coming to the battery needs to be regulated, because it's not, there's different, points of intensity of light. It may be cloudy, so you can't just hook up a regular battery that you'd buy from online that you can charge your phone with. You need to have something either in front of it that you can build your own, or for Voltaic, they have this own kind of hobby kind of IoT stuff, so their batteries can be charged from their solar panels. So that's important to keep in mind. The other thing is they have this feature called always on, meaning you will never turn off as long as there's a cord coming out and it's being discharged. This is important too, because for microcontrollers and Raspberry Pis, you generally don't want them to pull a huge amount of current, because you're trying to get as much use out of your battery as possible. So other battery packs will cut off when they see the voltage and the current dip, because they think the thing is charged. And so that would just turn your Raspberry Pi off if it's pulling that much low of a current. So that's another thing too. So their batteries are specifically designed for this kind of project I wanted to build here. So what's nerves? So if you saw the keynote, Frank went over it a little bit. I won't go into it for extended period of time, but basically I want to write Elixir, right? I don't want to have to worry about writing a bunch of startup scripts. I don't want to have to worry about customizing my Raspbian flavor or whatever it is on my Pi, on my SD card. I just want to write Elixir, and I just want to be like, okay, that's my project, now go. So Nerves, lets you do that. There's a platform. Frank talked about Buildroot in the keynote earlier. And specifically what this is that the image you generate, the firmware, is extremely small. It's between like 20 and 30 megabytes, and they're trying to get it smaller every day. So you can very quickly put this on an SD card. You can push it over SSH. They have Nerves hub now. So these things can update very quickly if you have a decent connection. There's a lot of Elixir modules that they include as part of the tooling. This is specifically when you want to SSH into your devices and you need to configure them. You can see how the network is configured and if you have network connectivity. And there's a lot of other tooling like command line tools that you need to be able to generate the firmware and configure devices. So in terms of firmware, so like if I wanted to persist data to the SD card, what does that mean? Is it read-only? So the firmware is read-only, but there's partition available if you needed to write configuration files or write data. And then this what's really super powerful about Nerves is it's hard to kind of break your device if you're updating and something goes wrong. There is a kind of blue-green deployment, like was mentioned earlier, of you write to the new partition, and if everything goes good, it now is pointed to that. If it fails, it can fall back into a good state. And particularly in my company, if we brick a device, because we do similar kinds of things, it's a huge pain in the butt. You have to get on a car, you have to go to some remote place a lot of times, and it could be several states away. So this kind of blue-green-like deployment with Nerves is really powerful. So this is kind of what happens. These are the steps. So you have your Elixir project here. It generates an OTP release. This is brought in with a Linux, the C libraries, the Erlang runtime. You specify your system. So I'm using, in this project, a Raspberry Pi Zero W. So I use the Nerves system Raspberry Pi Zero, all the Raspberry Pis, some Beaglebones, the kiosk module x86 one. That gets generated as a firmware bundle. And then you either burn that to your SD card, or if you can set up SSH, you can push it over Wi-Fi. So the first protocol I'm going to mention that I'm going to use is general purpose I/O. So these are just one wires or pin. You either set them to be an input or output. So you can write or read from them. On the Pi, when they write, to the Pi, so you're setting it to output. Anything that's near 3.3 volts is 1. Anything near ground is 0. And this is important to keep in mind because Arduinos and some other things, they can handle 5 volts, sensors. And there's a lot of sensors that use 5 volts. So if you have one, you have to use a voltage divider, either through a breadboard or however if you want to solder it, so that you don't wind up screwing up your Raspberry Pi. Whereas on the other side, if you read it, input, it'll read 1s and 0s. So you can set it to have it be in a pull-down resistor mode. This will be either the way you wire it up literally, or the sensors you get will tell you which way they'll need to be configured. So if it's set to pull-down resistor, when the circuit's closed, it'll read high, and then vice versa, if it's pull up, it'll read low when the circuit's closed. And I'll show you for the sensor I use, that's GPIO. So the first thing I'm going to be doing in terms of this being a weather-related thing is I want to see how much rain is falling. So a typical way of doing this is if you want to do this through a network or whatever, you have a tipping bucket rain gauge. I'll show you the code later. I'm going to write a GenServer to catch interrupts. When the bucket tips, it'll generate an interrupt. That means a certain amount of rain has fallen. And for these, typically it's this 0.2794 millimeters. This is a very exact amount of rain. And I'll convert that to US years as 0.011 inches. What's really cool too about this is that it uses an RJ11 telephone jack. It's just a way of wiring everything together. It's still GPIO, it's still 2 wires. But what's really cool is that this means I can get a really, really, really long cord, like a regular phone cord. I can extend it, and that was useful because the rain gauge is in a specific part on the back of my house, very far away from where the other parts are. And it's over 50 feet, and it works fine. I was really shocked at how easy this was. The one I bought was, I think, around $15, but the company I bought it from no longer seems to be selling them at the moment. But you can find them online. They're typically between $10 and $30. You can get nicer ones that are wireless. but they're fairly inexpensive. So this is kind of what it looks like without the cover. There's a cover here. You can see it on my roof. As the rain falls, it's going to cause it to tip that way, and then as more rain falls, it's going to cause it to tip that way. So you're going to get interrupts here. Here's the cord, and I've got a little breakout board just so I can put some wires, some male to female wires here. And this is actually not even my Raspberry Pi Zero. This is a Raspberry Pi 3, because I don't want to have to create a whole nerves bundle and prototype that way, right? I just want to see if the logic I wrote to catch this works. So that's another nice thing about these libraries I'm going to show you, is that you don't have to use a whole nerve system. You can just pull them in your regular Elixir project. And here I've got it on my roof. It looks pretty crappy, right? So I got a brick up here just to try and keep it flat, because our roof's really old and we're going to need to replace it anyway. So I didn't want to start nailing it or put a bunch of stuff on my roof anyways. So this is probably the least accurate thing of my whole system. You're supposed to keep these probably about 6 feet away at least from a tall structure, and the chimney's kind of right here. I don't really have a lot of space. It's a pretty steep roof, so it works well enough. It catches most of the rain, and I can compare it to local weather stations. It's mostly just to see, hey, is it raining a bunch at my house or not as much? And this is how it looks like from the top here. It kind of cones down, and there's these little holes right here. So like I said, a very known amount of rain falls when you get an interrupt. So for the other sensors, I'm going to use a different protocol. It's a little more complicated. It's I2C. It's integrated circuit. It's a bus. And so you get 2 wires where you get a serial clock and a serial data wire. But you may want to have a bunch of sensors, right, that are I2C. So what you can do is you can hook these wires up on a breadboard, and then you can read them all off the breadboard. You can have multiple sensors, obviously. I'll have 2 here. And they can respond to the bus. And you have to figure out what the register is, the address is, in order to be able to communicate with them. It'll be in hex. And I'll get into this a little more later, but what's really cool with I2C is you're typically writing blocks in binary data, and then you'll read a specified number of bytes back. And you'll get into this concept that I kind of had to figure out on my own that was really confusing, of basically the way the direction of the data coming back is when you read it. Is it one way or the other? So this is a concept called Indianness. So basically, it's the most significant bit or the least significant bit come first. And different sensors use different, they may be most significant bit first, or they may be least significant bit first, and that's where you have to reference the data sheet that they come with. So this is if you're using Raspberry Pis, this is a website called pinout.xyz. You can click on all these pins right here. This shows you the pin numbers, which are very important for GPIO and some of the other protocols. These are the 2 I2C pins you get. There's 2 more down here, but you don't have access to this normally. So I'll have 2 wires coming off here, and then my GPIO, I forget the pin numbers, but they're connected to some here. You've got a bunch of ground pins. You've got your 5-volt power pins, and then you also have a 3.3 volt power. So the 2 sensors I've got for this are they both do temperature. One does barometric pressure, and one does temperature. These are both pretty cheap sensors, too. You can get some much more fancy and expensive ones. In particular, this one I got, when you start doing this, you'll sometimes buy a kit of sensors, for $20. You get a bunch of these, and I think I had this one from several years ago, because this is a fairly old one, this BMP 180. But I looked online, it was $6 you can get. So that'll give me barometric pressure and temperature. The SHT31D is a little nicer and is a much more complicated way of interacting with it, because it can do a lot of different things. But this will give me temperature and humidity. And so since I have humidity and temperature, I can calculate the dew point, which I'll do in my project. And you can see here, you can either give this 3.3 volts or 5 volts to power this one. I think this one's only 5, so they kind of can differ. But you can see that they have both the serial clock and the serial data pins that you have to use. And so this is kind of what it looks like when I'm I got my sensor here for the BMP 180. This is a pretty intimidating looking thing for someone. I've never really wrote C++. I'm definitely not a low-level programmer. I'm just kind of trying to tinker with this. So there's a particular defined way of communicating with it. So for this one, I have to read, I won't go into all these details, but just to show you kind of what it looks like, there's all these configuration values you have to read before you can calculate what the temperature and the heat are. The temperature and the barometric pressure. And so this is what they gave you an example, but when you get your own device, these numbers will be slightly different, which is why it's important to pull this in. You'll go through this very intricate series of bitwise math, depending upon what the values are. And there's, like I said, there's a big long process. This goes on for several more steps. This is the SHT-31. This is one particular mode of doing it. There's some other stuff. You can see there's all these things like clock stretching. This is showing you what this most significant bit should be when it comes bad and what the least significant bit is. So this is the steps that you walk through of here's the command. If the clock stretching is enabled, it's this method, otherwise it's this, blah, 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 blah. So I bring this up to show you that this is not something where this was very difficult for me to interpret. And what even Frank at the training suggested was these data sheets can be very complicated even for people that do this. So a lot of times you're not going to find code that already exists for the sensor written in Elixir. But you probably will almost certainly find it in Python or C++. And if you can look at that a long enough time period, you can probably kind of work backwards from that, which is what I did specifically for the SHT-31. It has all these ways if you can turn a heater on to evaporate water and all this stuff. All I want to do is just read the temperature and the humidity for this sensor. So I found a Python library, and I was able to kind of piece it together and just say, hey, right, once a minute, just do this, instead of trying to go through 30 pages and look at all this pretty intricate amount of all the binary you have to figure out to write and read from. So in order to work with these protocols, there are these, it's a group of libraries called in the circuits, it's called circuits. There's one for GPIO, there's one for ISquaredC, there's two other protocols, SPI and UART that they also offer, so there are two different libraries I'm going to pull in here. There used to be a group of, it used to all be included in this project called Elixir Eel, and like I mentioned before, they split them all out, they added some features, and you don't have to put them in a NERVS project, so that's very useful to prototype with on your regular Raspberry Pi that's not running a NERVS system. And in particular, I don't need to do this, but I like pointing it out with the GPIO library. Before with Elixir Eel, when you get interrupts, it didn't give you a timestamp, and now it does. And this is very useful when you're looking at timing events. So, for instance, there's sensors that, like an ultrasonic distance sensor, where you look at the time it's fired and then wait for an echo to come back. And based upon the time difference, you can calculate the measure of distance that way. So that's something that is very useful when you're using these kinds of GPIO sensors. All right, so putting it all together. So up to this point, I've talked about here's what it looks like. It's pretty sloppy. So this is, I'm just kind of doing this as a project. I don't really care. Some people make nice, enclosures and stuff, but I just put it in like a Tupperware and cut a hole so that I can get the wire. The red wire is coming from the solar panel. This white one, as you can see, is the RJ11 that's coming from the rain sensor. Here's my battery. The battery's powering the Raspberry Pi right here. I got a bunch of wires hooked up. I can hook my sensors up off right here to give voltage and ground, and then all that's related to talking to the ISquaredC bus right there. And this is kind of how it looks like at the end. It's like even limping right here because I just bought, I didn't want to buy a fancy thing. I wanted something I could shove in the ground. It's got 2 spikes on it, and we've had a lot of rain, so it's kind of just leaning a little bit right now. I've got a little garbage lid on the top of it I found that I was trying to protect from the elements. And it works pretty well. It's pretty resilient even if it gets kind of wet. There's the solar panel. And then this other white cord right here you can kind of make out is coming from way around the other side of my house that's connected to my rain gauge. So that was all this little project right here. It's a the NERVS project that I made that's got all this. It's using MQTT to publish to a broker. I've got in an EC2 instance. It's just my personal AWS account. There's lots of them. I didn't care what it really was, if the broker was written in Elixir or not, because I just need to set it up. So one that's really easy to use is called Mosquito. It's written in Python, and you can set it up very quickly to get simple authentication so that only known things can publish to it and subscribe to it. And you can even use SSL. So I'm going to use this protocol, like I mentioned, is called MQTT, which is a pretty standard protocol in IoT. to use PubSub for these kinds of IoT projects. I've got a little DB project I made that will subscribe to this topic that's publishing this weather data, and then it's going to once a day do a daily backup job where it writes it to CSV, and I push it to an S3 bucket. And on this instance right here, just to save cost, I didn't want to spin up its own dedicated, it's just a simple Postgres database right there. And I've got a Phoenix project I'll show you later that also subscribes to the same topic. And I have a couple of live views I wrote to show the data coming in. And then I've got the database where the historical data is and some simple authentication stuff. So that is the whole project right here. And hopefully it'll kind of come together as I show the code. So everyone can see that. This is, let me start at 1 here. For nerves, you have a lot of configuration things you set up. So this is I won't go through every little last detail, but just show you real quick. This is the pin, the GPIO pin my rain gauge is on. These are those register addresses I talked about that you have to kind of figure out what they are for your ISquaredC bus. I gave it a time zone and the city IDs where they're related to a weather API I'm going to use just to show where I was. If I wanted to expand this in different locations, I could just to show you where the devices. Yeah. Is that good enough? Yeah, okay. All right, so this will be really big here. This is the GenServer I created to catch all the bucket tips, right? So the problem is that you may have a lot of rain coming down at one time. I only want to collect data once a minute, but I need to see how many times it tipped in that minute, if it tipped at all. So I will get a reference. This is just how you use the circuits library here for GPIO. I have to set it to pull up mode, and then I'll schedule collection, which down here just says, hey, after 300 milliseconds, I'll give it a little time to kind of set up, send a collect. And collect will detect rainfall pass the reference in, and I do this set interrupts, which if it finds an interrupt, if it sees it triggered, it's gonna write it to the mailbox, so I immediately have to then try and look for it. And after 2 seconds, I'll say, hey, just stop and then try again. Otherwise, I'll return this amount. This is the amount in millimeters that I showed earlier of how much rainfall came. And then for my API that's gonna call this GenServer, I will say, hey, get rainfall amount, either in inches or just in millimeters. And then I will reply, and then I'll reset my state to 0. Otherwise, to get inches, I'll convert it right here and do the same thing. So if it tips a bunch in a minute, I've tested it out. Generally, I'm not going to miss the tip, even if it's raining hard. So I'll hopefully be able to catch as accurate of a number as possible of the amount of rain that fell in that minute. Usually, it's going to tip once. If it's raining really hard, it may tip twice. Otherwise, if you poured a giant bucket of water on it, you could probably get it to tip several times in a minute. But even when in the hardest rains, it doesn't happen that frequently. This one I'm not going to go into too much, but this is just to show you how you use the ISquaredC library. This is my BMP sensor. You get a reference by opening it. This is the bus that you communicate with, ISquaredC1. And this is kind of showing you the power here of doing pattern matching with Elixir that you get, for free. Like I mentioned, you typically have to do a write-read. So I have to write some command, immediately read the data, and then do a sequence of steps on it. So I can say, hey, my value I know is going to be big Indian. It's an unsigned. It's going to be 16 bits. And I'm going to say, hey, write this command right here. It's binary and read back 2 bytes. That's how that works. And then there's a sequence of steps of getting the pressure, calibration, and then going through and doing all that math. I won't show that. It's the good thing is once you kind of figure this out once, you don't have to go back and write all this again. For the SHD, it's a little simpler. Oops. And this is really cool. I can say, hey, this is how you get the temperature humidity, is this command. I have to sleep for 50 milliseconds to let it collect based upon the sampling interval you give it. And I can say, hey, give me the temp 0 and 1 values that I need. Discard this, which is a acknowledgement byte. And this is the humidity information with another acknowledgement after it. And I can just immediately discard that and return this in a tuple. And then the last part is tying all this together. So I've got 2 I've got my two ISquaredC sensors, which don't have a GenServer. It's just code I write, and the other one is got a GenServer behind it. This is obviously my weather server. I'm gonna just say, hey, start I need to get references to these sensors. Then I'm going to say, hey, start a link to my rain server, so if it dies, it'll get restarted, or comes up to this GenServer here. Then I'm going to collect all this information. I'm going to round it down for my different temperatures, the humidity, the dew point I calculate, and then I'm going to pass it along. This is a library called Tortoise, which is very useful for MQTT and Elixir. This is my client ID. That's something that has to be unique, and I will publish saying, hey, I'm this client. I need to publish to this topic. As I mentioned earlier, we'll do a publish. This is a fire and forget kind of thing. The quality of service is 0. Just means I don't have to worry about saying, hey, I don't really care if for some reason the thing died. It's not a huge deal. Otherwise, you can give it different values to say, hey, wait for an acknowledgement, and then I can say, hey, that this was successful. I'll JSON encode it and just log it out. And then I'm going to try and schedule this once a minute. If I don't give it this kind of calculation, it'll start to drift. So it'll happen on like the first second, then the second second, then the third second, because this takes about half a second to completely go through. This is just to quickly show you what Tortoise is. It's pretty simple. You can use a supervisor this way. Here's my client, and I'm going to give it all this information to give it some authentication. And if you want to subscribe to topics, you can do so in this your child spec right here. But because this is the publishing, this is the nerve sensor, I don't need to worry about that. And then finally, just to show you what the application file looks like, I'm going to, in the main supervisor, start my weather server that's it's linking to the GenServer I have for the rain collection, and then also collecting the information for those two ISquaredC sensors, and then the Tortoise supervisor I just showed you there. And then you can give it based on if you're the host machine, what my development machine is, or the target. I can do things differently to work that way. And this is what the handler looks like for when you say, hey, I want to subscribe to a topic from this MQTT broker. You need to give it a handler. If you don't, otherwise it just logs the information. But if you want to do something with it, you'll say use Tortoise handler, and I'll handle a message from this topic right here. And I showed you earlier, I've JSON encoded it. And I'm going to get an API key just to collect what the weather is at my house based on that city ID I passed in. If I get a response, I'll decode it. Otherwise, I'll just trash it and say nil. And then I'm going to insert it into the database I showed you earlier. And that's all this does. I won't show you the code, but this also does the daily backup job. But the more interesting thing here is my handler in my Phoenix project. And it's the same thing where I got to do this, but I'm going to put it in an ETS table right here. This is my ETS repo, just so I'm not reading from the database every time to get latest data. And this was new to me. I don't do a lot of Phoenix work. I'm still kind of learning it, but Phoenix PubSub is a really awesome tool for this. Because I'm using 2 live views, but I don't want to query every time just to see if the data's been updated. I can use Phoenix PubSub and subscribe that way. So I've got my MQTT PubSub, right, for my topics, but then Phoenix PubSub's very similar, so it's kind of a natural fit. So I'm going to say, hey, I got some data. Anyone listening to weather data, I'm going to publish it. And this is just to show you real quick the ETS API I wrote just to shove it all into an ETS table here. I'm going to start that up. And then this is one. I won't show you the other one because it's much bigger and uglier. But this is the live view I have for the last piece of data I have. So if you're connected to the socket, I'm going to subscribe to weather. So I'm just going to use Phoenix PubSub and say, hey, listen here. When I get a weather update, I'm going to put the data into the socket, and I'm going to do this by getting it from that ETS repo. Oh yeah, I had something else here. I won't go into that. But basically, this is all the temperature and other sensor data and the time that it came in. So hopefully, I'm going to show this off real quick. Let's see. That's going to take, 50 seconds. You'll see this update right here. This is the last piece of data I've got here. So this is literally happening at my house right now. You can see it's in Eastern time. I live in the Atlanta area. So this is the dew point that's being calculated, the humidity, barometric pressure, and then these are two different weather sensors I have, or the temperature sensors. You can see there's a little difference, but they're pretty consistent. That's not uncommon. One's maybe more sensitive than the other. And in 20 seconds, we'll just wait here. You'll see that because I'm now on that view, I'm subscribed to the socket, and you'll see it push data come through, and you'll see these values change. There you go. So there you can see it pushed right there. And I obviously have got some more. Yeah. So that's pretty simple, right? So obviously I want to see more historical data. So I've got in this view right here for the hour, this is using a simple chart.js library. So this is still using Phoenix Live View, but you can do all these mount hooks you get, all these hooks you get. So when it's mounted or when it's updated, I can update the chart. So let me show you throughout the day. Here, starting at, I guess, yeah, see this is confusing now because this is converting it to time in Pacific, but this would be midnight East Coast time. So you can see it got down to here, and this will update too, but this is a 10-minute average over time. And let me just double check. So you can see the humidity, it's been raining a bunch, so it's obviously basically almost completely, saturated at nighttime, and then it drops. You can see dew point here. If you don't know what dew point is, it's kind of the measure of how close the temperature is with how much water is in the air. And typically when your dew point gets to the actual temperature, it's very, very muggy and humid, particularly in the summer where I live in the Atlanta area. And this is barometric pressure. That's kind of useful when weather patterns change. You can see barometric pressure change pretty drastically, like when a thunderstorm rolls in. And this is rainfall, so I can go back and bump this. I know we got some rain the other day. So this is throughout the day. I can see this is basically, this 0.01 is one tip in a 10-minute span. I'm not going to add it all up right now, but you can see it rained a bunch. I can go back here. So when I do this will send an event down, and my live view will update. And then monthly, I'm trying to look at the high-low temperatures right here, so I can go back to February. And that'll update, so I can see the low was 42. There's a bug in here, but it's on the chart. The low was 42, the high was 66. This is in Fahrenheit. And you can see the temperature's been kind of rising. We had some really bad, cold days, and so yeah. So that's basically it.
We've got plenty of time for questions.
Oh, yeah. Yes. Yes, my code is all online.
Okay.
So this is the NERVS code. This is that simple database application. This is Weather Station. NERVS and Gadget, I guess it's now being deprecated because there's a new thing, but this is a very simple project you can use to boilerplate all your NERVS code. Highly recommend it, and I think I don't know what the new one is. I know Frank was showing us the other day, so, but that was one I used. This is the Circuits Libraries, and if you're interested in NERVS, it's nervs-project.org.
Yeah, I was talking about your code.
Yeah, my code is all these first three right here.
Okay.
Yeah. Yes.
So just curious why you're using the Pi0W. Was that power related? The reason I ask is you have a single core Pi on there now, but you obviously have supervisors, so you're running on one scheduler. So yeah, you said it's a power.
The Pi0W is by far the lowest. I'm using a package I showed power. You're probably familiar with Power Control, so I'm trying to get it as low as possible. Also because at that training we went to, we got Pi0W, so I was like, I just have this left over. I'm going to use it. So yeah, if you get really squirrely, you can put Phoenix. You can make a specific project called a Poncho project. So there's no reason why you can't put Phoenix applications on your in a NERVS project to look directly at the device. But I wanted to do something different and push it to the cloud. So.
Okay, I've got a question here. Elixir Eel, you were talking about a replacement for it?
Yeah, all those circuits libraries, it used to be under this project called Elixir Eel. And I guess that's been a little while now, but so if you want to, so this is how this project you would use to do GPIO, ISquaredC, SPI, UART. So they broke them out to make it, I guess, more maintainable
Okay.
into a bunch of different projects. Yeah.
Okay, that made me smile. Yeah,
Yeah.
it originally came from Erlang Ale,
Oh.
which was a project we kicked off a long time ago, which
Really?
Frank then took in and then migrated over.
Interesting.
Yeah. So
Yeah, that's cool.
It's great to see it lives on.
Yeah.
Yeah. Yeah.
Do you have any recommendations for like how to learn the electronics part of it and how to communicate
Yeah.
with the devices? Because that's in the Nerves projects I've played with. That's my
Yeah.
stumbling block.
Unfortunately, I didn't have enough time to kind of walk you through how you do all this. So, once you mess, I think what I would first say is, if you're kind of struggling to, hey, I want to write all that crazy binary, pattern matching stuff. First, look, there's a million guides online for all these sensors that are probably going to be written in Python first. They'll probably walk you through how to set it up. You'll probably be installing Raspbian. And then after that, you can maybe start to get an idea of, okay, this is what they're doing. I know they're writing this, they're reading this amount of bytes, they're doing all this stuff. Go look at the data sheet. Even if it is a little intense, they're usually, once you kind of look at it for a while, that BMP one was very complicated looking. There was a lot of math, but it's actually a very straightforward process. If this, then do all this bitwise math. Otherwise, go here. And yeah, there's probably enough, and it's not the best, but there's definitely enough blog posts I would look at of, hey, let me see, did someone publish anything about how to work with any kind of sensor that uses ISquaredC? GPIO is a lot more straightforward, but ISquaredC is probably the more complicated one. I'm going to look, hopefully they'll walk you through it. I'm going to try and write a blog post myself. It's been a while since I even wrote a lot of that code, so I'll be sure to announce that. Yeah, so that's kind of how I did it. I found a bunch of stuff in Python, and I was like, okay, I think I know enough now. I could probably kind of go backwards from this.
What about the wiring up of everything?
Yeah.
The actual circuits themselves and resistance, how much voltage?
Yes, for like the sensors, you don't typically need to worry about like putting up, like, unless it's a 5-volt sensor and there's nothing there, you don't need to worry too much about worrying about adding a resistor between it. But all you got to do is like, I'll type like voltage divider, 5-volt. So I can probably find, so there's let me see, fritzing. So you'll find a lot of pictures. So fritzing is a thing you can use to draw this out and diagram it, and you can find lots of things. So they're probably using a voltage divider here. So there's 2 resistors and parallel. This is some other thing, but you can just Google it. Typically, you don't need to worry about that, but that's the only thing I had to really do was just add a voltage divider. The rest is, okay, take the pins from the ISquaredC bus, put them on this line, and then everything else can read off of that. So then I can just take it from my sensors and do that. Yeah.
Any other hard questions? Okay, let's hear it for John. Thank you so much.
Thank you.